Hello everyone, my name is Zhen. I'm a PhD from the University of Texas at Arlington. Today, I'm excited to present our recent study on emerging hardware-managed tier memory, specifically focusing on Samsung CXL Memory Module Hybrid (CMM-H). This is a collaborative effort with the Network and Distributed System Lab at Hewlett-Packard Enterprise. So modern computer systems increasingly rely on tier memory and storage hierarchy to balance performance, capacity, and cost. Typically, this system combines a fast but expensive performance tier such as DRAM with a slower but larger capacity tier such as non-volatile memory, SSD, or hard disk drive. The idea is to cache hot and frequently accessed data in DRAM while moving cold data to the slower capacity device. This approach helps applications run faster without requiring all data to fit in DRAM. Traditionally, tier memory has been managed in software. As shown in this diagram, the DRAM layer is used to cache hot data. When the requested data is not presented in DRAM, the system fetches it from the SSD through block I/O. This data movement is typically triggered by software mechanisms such as page fault. While mechanisms like mmap allow applications to access large files as if they are in memory, they still rely on operating system to handle page faults and issue I/O requests. This software patch introduced noticeable overhead. With the emergence of Compute Express Link, we now have a new way to expand memory hierarchies. CXL is a high-speed interconnect that allows CPU to directly access memory in external devices using ordinary load and store instructions, even if that memory is not connected through the traditional DDR bus. This enables a new class of hardware, including CXL Type 3 memory expanders. Samsung CMM-H is a CXL Type 3 device that integrates both DRAM and NAND flash together. Internally, it uses DRAM as the performance tier and NAND flash as the capacity tier. This device is managed by a cache controller and presents a byte-addressable memory interface to the CPU using the CXL.MEM protocol. In theory, this means applications can transparently access data stored on SSD with ordinary CPU instructions without relying on software tiering mechanisms. In this work, rather than just performing basic performance measurements on CMM-H, we focus on a detailed comparison between software-managed and hardware-managed memory tiering. We use CMM-H as the representative hardware solution. Beyond that, we conduct a deeper analysis of cache miss scenario, uncover critical performance characteristics, and identify key limitations in the design of CMM-H. Here we highlight two main observations. First, cache hits are fast, but cache misses are painfully slow. The figure on the right shows this clearly. With CXL.MEM, when the CPU hits the L3 cache, the access takes just tens of nanoseconds. If it goes to DRAM on the DDR bus or the internal DRAM inside CMM-H, the latency increases to hundreds of nanoseconds. That's about a 10 times gap compared to L3 access, which is still manageable. But if the access misses the DRAM entirely and falls to NAND flash, the latency drops to tens of microseconds. That's about 1,000 times slower than an L3 hit. And it gets worse because CXL.MEM is a memory interface. These flash delays not only store the CPU, they also prevent the stored CPU from yielding its resources to other processes. In other words, the penalty isn't just long latency, it also wastes valuable CPU cycles that could have been used elsewhere. Second, when the cache hit ratio is not perfectly high, software-managed tiering often outperforms hardware thanks to asynchronous handling, flexible promotion granularity, and more effective use of system resource. Before demonstrating our result, let me introduce our testbed. We conducted all experiments on a server that equips Intel Xeon Platinum 8556 processor, and we use a FPGA-based Samsung CMM-H prototype. In our experiment, we compare CMM-H with directly attached NVMe SSD PM9A3. This slide illustrates how CMM-H handles memory requests from the CPU. When the CPU issues a memory request, it first goes to the CXL endpoint inside CMM-H. From there, the cache controller checks if the requested 64-byte cache line is already in the DRAM cache. If it's a hit, things are straightforward. The cache controller simply returns that 64-byte cache line back to the CPU. But if it's a miss, the story changes. Because CXL.mem is a blocking memory interface, the CPU has to store and wait. At this point, CMM-H issues a 4KB read to its internal SSD. The latency of that read can vary from about 20 microseconds up to 80 microseconds. And here's where amplification comes in. For a load miss, fetching 4KB data to satisfy a 64-byte request results in read amplification. For a store miss, the system must perform a read modify rate, which adds even more overhead. Once the SSD data comes back, CMM-H fills the DRAM cache with that 4KB block. If the cache is already full, some dirty cache line may have to be evicted back to the SSD first. Finally, after all of that, the 64-byte data is returned to the CPU. After introducing the basic architecture of CMM-H, let's now turn to its performance. We evaluated it using a single-threaded sequential access workload under two scenarios, cache hit and cache miss. For the cache hit case, we first pre-warm the internal DRAM cache of CMM-H so that subsequent accesses to the same addresses would consistently hit in the DRAM cache. We then compared its performance against a directly attached Micron CXL memory module, as shown in the top figure. CMM-H cache hits deliver bandwidth very close to CXL memory module for both load and store operations. For the cache miss case, we explicitly evicted data from the internal DRAM cache before measurement, ensuring that each access would fall through to the underlying SSD. Here we compare the performance with a directly attached NVMe SSD. The result is striking. Bandwidth drops sharply, performing even worse than the NVMe baseline. The reason is that directly attached NVMe supports asynchronous non-blocking I/O, while CMM-H exposes only a blocking memory interface. As a result, every cache miss translates into a synchronous NVMe read from its internal SSD, making each miss extremely costly. And if we compare a software solution with the hardware solution, things become more interesting. In this experiment, each thread accesses 512 MB of data. We tested three setups. First, CMM-H, and we evict its DRAM cache at the beginning. Second, an MF file backed by a directly attached NVMe SSD with prefetching disabled. Finally, the same MF file but with prefetching enabled. As the figure shows, CMM-H delivers the lowest bandwidth because every miss results in a blocking NVMe read. With mmap and no prefetching, there's a bit of improvement as thread scale, but the gains are still limited. In contrast, once prefetching is enabled, performance jumps dramatically. With only 4 threads, mmap with prefetching achieve an order of magnitude higher bandwidth than CMM-H. This is because with software prefetching, software can leverage the asynchronous I/O interface to achieve the full bandwidth of directly attached NVMe SSD. However, due to the blocking memory interface and the lack of hardware prefetching, every CMM-H cache miss translates into a synchronous NVMe read. For more detailed results, please refer to our paper. Here, I would like to share the insights, suggestions, and future directions from our study. First, cache misses are extremely costly. What makes this worse is the blocking memory interface of CMM-H, which stores the CPU on every miss and amplifies the penalty. Second, hardware-managed tiering does simplify management, but it lacks flexibility. In contrast, software-managed tiering enables asynchronous cache mishandling, allowing computation and I/O to overlap, which leads to better utilization of CPU and SSD resources. Third, an important takeaway for application and system designer is the need to design for locality. Improving temporal and spatial locality can greatly reduce cache misses, significantly improving the performance of CMM-H. Finally, looking ahead, we believe the most effective direction is hardware-software co-design. By combining hardware's speed with software flexibility, we can develop smarter cache miss handling mechanisms and fully realize the potential of CXL-based hybrid memory. To summarize, we study the performance of hardware-managed memory tiering in Samsung CMM-H with a particular emphasis on cache miss performance. We also carry out a comparison between hardware-managed and software-managed tiering, showing both the strengths and weaknesses of each approach. Finally, our study reviewed key limitations of hardware-managed tiering and provide insight for future directions. Thank you all for listening, and I'm happy to take questions.